Good morning. Myself Naveen Kumar Saini in the course Antenna and Wave Propagation. Today we are going to discuss about the short electric dipole. So first thing which is very important about the short electric dipole, so that is a very infinitesimal uh, test dipole. Okay. So for that definition, what is that? So any linear antenna which consists of large number of short conductors connected in series. So in this diagram, we can see that when this one is the transmission line, and when this transmission line is flared at the terminal, so we call it as the dipole. Okay, or we can say any kind of antenna. So here we see how this shape is looking like. This is because of accumulation of the positive and negative charges. Okay, so this is equivalent diagram of this circuit is this one. So when we provide the any AC at this terminal at the transmission line, so because of this applying this AC positive and negative waveform of AC, so because of that one the charges are in motion along this wire. Okay, so because of the motion of the charges, the acceleration or deacceleration occurs into the charges. So because of that reason, this accumulation of charges occur at the extreme end terminals of this wire. So this accumulation of this charges is equivalent to the positive Q charge, and accumulation of charges at this terminal is the negative Q charge. Okay, so in this way the current is flowing in this direction from negative to positive side, and we are assuming that the length of this dipole, this is the L. So our question is how to find the electric field or the magnetic field, or in sum up we say the field strength of the short dipole. So in this case how we look like, so we are placing this dipole, so just like this dipole, so we are placing this dipole along the z axis. Okay, so this dipole, and what we want to find the electric field or the magnetic field, all the fields at the far distance from this dipole. So in this way, we are taking the geometry of the spherical coordinate system where the variables are r, theta, phi. So we have studied already in the electromagnetic field theory that any point in the spherical coordinate system can be represented as the r, theta, phi, three variables. So what is the r? R is the radius of the sphere. Okay, so radius of the sphere, and theta is what? Theta is the angle from the z axis to that particular line which is connected from the center to the particular point. And phi is nothing but this is a horizontal angle. So how we are getting this horizontal angle? We take the projection from this particular point and we project it on the xy plane. So when we connect this origin to this particular point, to this projected point, so this angle from the x-axis is the phi. Okay, so here small r is the radius of this sphere, or the radius or the distance from the origin to that particular point at which we want to find the electric field or the field, to measure the field. Theta is the vertical angle from the z-axis, and phi is the horizontal angle from the x-axis. Okay, so this is the geometry how it looks like, and capital L is the length of this dipole, and it is placing at the center of the xyz axis. Here we see because of the electric field, if you are finding the electric field, what is the direction of electric field? Electric field is nothing but this will be there will be the three components of electric field: ER, AR, E theta, A theta plus E phi, A phi. Okay, so what is the ER? ER is in the direction of R, so this is the ER. E theta will be in this direction. Okay, because direction of theta is from the z axis. Okay, so this will be the component of electric field in the direction of theta, and E phi is in the tangential component. This is the horizontal tangential component at the particular point P. Okay, so this is the representation of ER, E theta and E phi. Similarly, we can find the value of HR, H theta and H phi, which will be which we have to take care when we will find the value of H. Right now we are just simply representing the value of electric field. So here the effect of the instantaneous current, by the geometry we know that electric field current I is equal to I naught e ki power j omega t. So this is the instantaneous current which is given which is flowing into this dipole. Okay. Now the another concept which occur into this antenna theory, that is the retardation effect. So what is the retardation effect? It is representing the at what time when we provide the current into this dipole. So at what time, so we are observing the electric field or the magnetic field at some point P. So the time delay from this point to this point is nothing but it is because of the retardation. This is because of the retardation effect. Okay. So it's not like when we provide the current at one instant of time into the dipole, and in the same time we are observing the far field at the point P. So this is occur because of some delay. Okay. So this delay occurs because of the retarded effect. Okay. So because of that reason we represent this current I into the retarded current. So we represent this current, retarded current in terms by representing the square bracket. So square bracket of I is equal to I naught e to the power j omega. So in place of t, what we write? We write the t minus r upon c. So this factor t minus r upon c is nothing but because of the retarded time. Okay. So t minus r upon c. So everywhere wherever we represent this retardation effect, so we use the, in place of t we use the t minus r upon c. Okay, so now for the magnetic vector potential, so A is magnetic vector potential. Okay, so we are trying to solve to find the electric field. So we will use that formula for the electric field by using the Maxwell's equations. So in that Maxwell equation we require the two type of potential. First one is the magnetic vector potential, and second one will be the scalar potential. Okay, so the condition for this dipole is what? That the R is very much greater than L. R is what? Small r is the distance from the from this origin from this center of this dipole to the particular point P at which we want to find the far field. So this distance r is very much greater than the length of this dipole, because this this dipole is a infinitesimal small. So that is why the condition we are applying, R is very much greater than L, and the wavelength is also very much greater than L. Okay, then the distance s of an element dz from the point P can be taken as what we are using. We are using this this element. The length of this element is dz, and the distance from this element to this particular point is the s. And we are taking the S1 is from the top of this dipole, and S2 is from the bottom of this dipole. So in this way the magnetic vector potential will be Az is equal to mu naught upon 4 pi I upon R. So this is what this current is representing as a retarded current. Okay, so because this retarded current is we have already discussed in the previous slide. So here we are integrating the dz only. We are taking this one outside and here. Okay, so s for the far distance, s and r will be same. Okay, so that is why they have taken the s is equal to r, and we are taking out r outside. So when we are integrating, then the magnetic field magnetic vector potential will be mu naught I upon 4 pi r into L. So in place of retarded current, we are using this formula, e to the power j omega t minus r upon c. So in this way, the magnetic vector potential will be Az. So now come to the retarded potential. So as I said, there are two types of potentials we have to consider. First one is the A, which was the magnetic vector potential, and second one is the V, which is the magnetic scalar potential. Okay, or the scalar potential. So retarded potential for the charge distribution we represented as the V is equal to 1 upon 4 pi epsilon naught integrate rho upon s into tau t. Okay, so again we can represent this density or retarded charge density as the rho is equal to rho naught e to the power j omega t. In place of t we are using the t minus s upon c. As I said, r and s are same for the far distant. Okay, so in this way we can represent that. So I don't think there is any issue into that one. So how we are getting this? Basically, this we know this formula that V is equal to Q upon 4 pi epsilon naught, okay, into R. Okay, this formula we are aware about that. This is because for the only 1 point charge. Now, if we have the density of this charge density, if we in place of Q we have charge density, how we can represent this charge density? We can represent this charge density as the rho into dV, right? So this is rho into dV. So what we have done, we have just put it this in place of Q as the rho. So in this rho here in place of dV we have written as a d tau, in which is an infinitesimal volume element, and epsilon naught is very much known to us, that is 8.85 into 10 to the power minus 12. So now we are using the geometry for solving these equations for these conditions. So how we are taking this? So here this is the dipole, and this one is the S1 and this one is the S2, and this is R. So we are we are changing S1 and S2 in terms of the R. So what will so in this way this is the theta. So when this is theta, this is also theta. Sorry, this is also theta. So when these two are theta, so in this case this is the L and this one will be L by 2. So what will happen? So in this case this will be what? L by 2 cos theta, and similar to that this is also be L by 2 cos theta. So now what will be the S1? S1 will be what? This is the S1. This is complete R. So S1 will be what? R minus L by 2 cos theta. So similarly we can find these equations that S1 will be R minus L by 2 cos theta, and L2 will be what? This will be R plus L2 by cos theta. So I hope this point is clear to all of you how we are getting this. Okay, so here what we are using for these two charges, because we said this is the minus q charge, minus q charge, this is plus q charge. So the total potential difference because of these two charges will be 1 upon 4 pi epsilon naught q upon s1 and minus q upon s2. So now we are using the dq upon dt is equal to I. So dq value will be I dot I into dt. So in this case the retarded charge will be I into dt. So in place of I we can put the j omega t minus r s upon c, because r and c are same. R is equal to s. So in this way, so when we are integrating this, so this I naught and e to the power j omega t minus s upon c will be outside. So when we are integrating this, what we are getting, j into omega into definition into the denominator. Okay, so this is the this is nothing but this is the difference integration. So s1 s2, so we will put the value of s1 s2 into this equation, and q from here into this equation. So when we are putting all these three equations in these values of q1, q, s1 and s2 into this equation, so the potential will be equal to like this: I naught upon 4 pi epsilon naught j omega e to the power j omega t minus s1 upon sc upon s1 minus e to the power j omega t minus s2 upon c upon s2. Okay, so this is your this is the potential. So what we are using now, we will put the value of S1 and S2 into this equation. So when we put this S1 and S2 into this equation, and we are taking this one as denominator, as we're combining this as solving this one. So R minus T upon T by 2 cos theta and R plus L by 2 cos theta. So when you're solving this one and just applying this condition, where the L2 cos square theta by 4, L square cos square theta by 4, which comes in denominator, has been neglected. Why we are neglecting this? Because value of R is very much greater than L. Okay. So when you're solving this one, so in this case, the L square cos square theta by 4 will be neglected, because the value of R is very much greater than. Okay. So I can write it, if you are getting some confusion, that when you're solving this, the R square minus L by 2 cos theta whole square. Okay. So when we are comparing this R square and this one, so we know that R is the distance at which we want to find the electric field intensity. So that value of R is very far. So when R is very far as compared to the length of this dipole. Okay. So in this case, we can neglect this one, because cos theta maximum value is 1. So it means this whole value is very less as compared to R. So that is why we have simply taken the R square here. Rest the things are same. We are taking this one in the same way. I mean, we are not changing it. But now we are again solving it. How we are solving? We are just simply changing e to the power j omega. So this equation we can represent as, we know that e by jx is equal to what? This is the cos x plus j sin x. Okay. So we are converting this equation in this one into this form. So we are not converting this equation in this form, then we will get this one. Now we will apply some trigonometrical geometry by using the condition like lambda is very much greater than L and the R is very much greater than L. So in this way, just take this one, because this is the same value. So we are getting this omega L cos theta upon 2c, right? So we know we are converting omega is equal to 2 pi f and L cos theta upon 2 lambda. So in place of c, we are using the lambda f. So after solving this, we have come to know that pi L cos theta upon lambda. So we know that lambda is very much greater than L. Okay. So by this condition, this value will be very less, right? So if this value is very less, so if we assume cos theta, or the theta tends to 0, so cos 0 is 1. So we are representing this cos function is as equal to 1. Now come to the sine function. So for this sine function, we know that sine theta or sine phi is equal to phi when phi is very much less than 1. Okay. So we can use this geometry. So sine omega L cos theta upon 2c will be equal to omega L cos theta upon 2c. So now substitute these two values, cos and sine, into this equation. So we will get v is equal to I naught L cos theta e to the power j omega t minus r upon c upon 4 pi epsilon naught into c, and this equation we are getting 1 upon r plus c upon j omega into 1 upon r square. Okay. So two things we have covered. One is the magnetic vector potential and second one is the scalar potential. Okay. These two functions we got that. Now we will apply these two functions of magnetic vector potential and the scalar potential into these two equations. So by solving the electric field for the short dipole, we know these two Maxwell's equations, E is equal to minus j omega a minus del v upon del v, and second one is the H is equal to del cross a. Okay. So we have to write it as the 1 upon mu as well. Okay. Because we know this formula, v is equal to del cross a. Okay. So H will be equal to del cross a into 1 upon mu naught. So by using these two equations, and we will put the value of A and V, which we have just derived in the previous slides, we will put into these two equations, 11 and 12. So for solving that, we are taking the polar coordinate for vector potential A. So A can be represented as the RAR and plus theta A theta plus phi A phi. Okay. So but we already gone through that how we write this type of vectors. We write it as the AR into AR. Okay. And A theta into A theta and A phi into A phi. Okay. So this AR, A theta and A phi, these are orthogonal coordinate system. So we can use R here, or we can write the R theta, or theta in place of A phi we can write the A phi. So here this guy has written like that. Okay. So now the A value will be like this. So come back to our main question, because we want to know the value of we know what is the electric field. Electric field, we write it as the AR, E theta, E phi, A phi. It means we have to find the components in the direction of R theta phi, and H can be written as HR, AR, H theta, A theta, H phi, A phi. Okay. So if we want to find the value of E and H, so we have to find the each component in the direction of R theta phi. So if we are taking the ER component, in this case we have to take the AR as well. If we are taking the E theta, then we have to take the A theta. If we are taking the A phi, then we have to take the A phi here. Okay. So in this way, for this way we are taking the magnetic vector potential. So as we know that dipole is lying in the Z direction, right? Dipole is lying in the Z direction. So the vector potential will be AZ in the Z direction. So this AZ is in the Z direction. So it means that there will be the two components for this resultant. One will be like this one, the second one will be like this. So these two component resultant will be this AZ component, right? So this thing, what is this component? So this component is nothing but this is the A theta component, right? And this one is what? This component is nothing but this is the AR component. I hope this point is clear to all of you. So now we can write the AR. It means there is no A phi component into for this AZ, right? So for this AZ for this AZ direction, there are two components. First one is this A theta component, and second one is this one AZ AR component. So in this way we have two components, A theta and AR for the AZ. Okay, so in this way we can write AR we can write the AZ cos theta, and A theta we can write the AZ sin theta with the minus sign, because direction of A theta is what? Direction of A theta is from the Z axis. If this one is the Z axis, so this is nothing but this is the theta. So this direction is theta. That is why they have taken the A theta in this downward direction. So this point is clear to all of you. So AR and A theta we can write in this way, right? And we are already aware that what is the AZ and A we have just derived in the previous case. So when we put the gradient, we find the gradient of V, right? So what we are doing? We are taking the gradient of this potential, and then we will take the A and we apply with the j omega. So first we are taking the gradient of the potential in the spherical coordinate system. So this is the formula for that. Electric field we are aware, because there is no E phi component. A phi is not there, so A phi is 0. So when the A phi is 0, it means del V upon del phi will be 0, and it means the E phi will be 0. So what it shows, the electric field component will have the only E R and E theta, not the E phi. Okay. So that is why this electric field will be written as AR ER plus A theta A theta. So with the help of these equations, we can put all together then ER will be equal to minus J omega AR minus del V upon del R. So what we are taking? We are taking the, for this one we are taking the only the AR component for this. Okay, so we are taking the AR component. So in place of A, what we will write? We will write the AR, and this will be the del V. This is a scalar potential. Okay, so del V upon del R, we are simply writing AR in terms of AZ cos theta and del V upon del R. So E theta will be what? E theta will be A theta 1 upon R del V upon del theta. So this equation will be like this one. Okay, so ER and E theta we can use that. So now we will put the values of all which we just got it about the AZ and V. When we put all these values all together, then the electric field in the direction of R will be this one. For calculation you have to do that, and E theta will be like this. So we see that ER is the combination of 1 upon R square plus 1 upon R cube, right? So these two terms are there, and E theta is again ER, R square and the R cube. Okay, so these factors are very, very important to take care. Okay, so these are the measured electric field in the direction of R and in the direction of theta. So there is no this electric field is not in the direction of phi. So now next is the magnetic field for the short dipole. So formula is the same as we have just discussed, that H is equal to 1 upon mu del cross A. So we will take the del cross A in the spherical coordinate system again. So this is the formula, but you must be know about the in the matrix form. Okay, so here A phi is 0. Just simply put the A phi is 0, and we will get the value of H in the direction of phi. So this will be I naught L sin theta e to the power j omega t minus r upon c upon 4 pi and j upon c r. Okay, so r is here and r square is here. So here when we take A phi 0, so automatically HR and H theta will be 0. Okay, okay, so HR and H theta. So we can see it here that A phi is 0 and del upon del phi is 0. So it means the HR will be 0, right? So here it's as well we can see that del upon del phi and A phi both are 0, right? So this is 0, this is 0, this one is 0 and this one is 0. So when these all 0, so it means what will left? Only the H phi will left. So in this way we can write these equations, right? So if we see that all equations which we are getting the equations for the far field. So we see come here again. So for the far field, right? So these two are the at a distance of R electric field. Now for far field, what will happen? R is very much greater than, right? R is very much greater than. So if R is very much greater than, it means this value will be what? Tends to 0. You're the very small. And if R is very much greater than, so it means this value is also be 0. So it means we are not getting the ER for the far distance. Okay. Similarly, if we come to the E theta, so if R is very much greater than, it means 1 upon R square will be again 0. We have to neglect this, and again 1 upon R cube, this also be 0. So what will left? J omega c square into R. Only this term will left, but this term will be cancelled out or neglected. Okay. Similarly, when we come for the H phi, so in the H phi for the far distance, so which term is 1 upon R greater than 1 upon R, means 1 upon R square, 1 upon R cube, 1 upon R cube 4, like that. So all those terms will be neglected. So if we see for this term, this one will be 0 for far field. So this is the conditions for the far field, that the one up if in denominator power is greater than 1, though we have to neglect those terms. So when we are neglecting all these terms, then the finally case which we are getting, that is the E theta and H phi. Okay. So for the far distance, E theta and H phi, these two terms will be observed at the far distance point P from the short dipole. Okay. So in this way, we can find the intrinsic impedance of the free space. We know this formula. Intrinsic impedance is nothing but the E upon H. If E is in the direction of theta, then H will be in the direction of phi. So in this case, power radiated in the direction of R. Okay. So if we see the point P, so where the point P was at the distance of R. So it means the power radiated will be in the direction of P. So that is why we have taken the E theta upon H phi. So this is the intrinsic impedance. So we are just simply taking the E theta and H phi from these equations. When we are combining these, when we are dividing this equation E theta and H phi, so in this case what we will get? We will get only very simple expression, that is 1 upon epsilon naught into C. So this is the mu naught upon epsilon naught. This value is 377 ohm. So this is the intrinsic impedance for the free space, or we say this is 377 ohm or 120 pi. So when we talk about the radiation pattern for this far field region, so we can see that E theta is in terms of sin theta and H phi is also in terms of sin theta. So where the direction, where the maximum electric field will be there. Okay. So what is the procedure? We just simply normalize this electric field by this component. So what will left? Only the sin theta. So what is the value of sin theta? Maximum. So when this will be maximum, theta is equal to 90 degree. This is E will be maximum. When E will be minimum? When theta is equal to 0. Okay. So electric field 0 means power will be 0. So we can see in the direction of 90 degree, electric field is maximum. At the distance, angle of theta is equal to 0 degree. In this case, the power electric field will be minimum or 0. Okay. So we are observing the null point. We are observing the null point at this point, right? And the maximum radiation pattern will be in the direction of when theta is equal to, this one is a theta, that is equal to 90 degree. Okay. So in this way, we draw the radiation pattern for the short dipole, where this is the dumbbell shape or a dot net shape is here for the short dipole. Okay. So this is the end of this lecture. I hope you understood how to draw this radiation pattern for the short dipole and how to find the far field electric and the magnetic field, which is the E theta and H phi. Thank you very much.